Hi guys, you're in Ask Your J channel, and for this video, we are going to learn how to solve a partial vaporization problem containing more than two components. We have here a flash, or what we call a partial vaporization calculation for a mixture containing more than two components. If you have watched my video on the estimation for the dew point and bubble point temperatures and pressures, you can see here in this problem that I am still using the same composition of the mixture. So I have here a liquid mixture containing 25 mole percent N-pentane, 45 mole percent N-hexane, and 30 mole percent N-heptane as initially at 69 degrees Celsius and a high pressure. So for this one, I will assign the components as according to numbers, okay, to help us be guided in our assigning of variables. So the temperature is initially at 69 degrees and a particular high pressure. To perform the partial vaporization, we need to lower down the pressure inside the flash drum in order to form the vapor phase. And for this one, this kind of flash distillation process is isothermal. So the temperature of 69 degrees Celsius is maintained inside the flash drum, and the pressure inside the flash drum is around 1.013 bar or 1 atm. So our goal is to find the relative amounts of the vapor and liquid in equilibrium, and of course the compositions. So we use the following K factors, and the assumption here is that the vapor and liquid phases are in ideal state. So they follow, okay, the K factor is related to the Raoult's law by this equation over here. So we are going to use this one later when we establish the equations. So take note that this is multi-component. So we are going to establish a lot of algebraic equations, and we are going to solve them simultaneously using Excel. So we are going to try our best to get the correct answer for this one. So let's start. So first things first, we need to create a schematic diagram, just a simple diagram to organize our variables, our knowns and unknowns. So we have here a box or a block to, signify a process. We actually do not have a feed, right? We don't actually have a how they call this, the amount of feed in the stream. So we can just declare a basis. We can just use 1 mole of the feed for this one. Okay, of course, in chemical engineering calculations, you can just use any basis. Yeah, any kind of basis, and then you will still get the same answer. So our feed is 1 mole. So we have F equals 1 mole. And then our initial feed is a liquid mixture. So since this is a pure liquid mixture, the usual thing that I do is I use the variable z to assign the mole fractions of the components inside a mixture that exists as a single phase. So for Z1, we have 25%, so we have 0.25. Our Z2 is 0.45 N-hexane, and our Z3 is 0.30. Okay, so of course, at a temperature of around 69 degrees Celsius, and we have a pressure of 1 atm. Okay, so we allow the mixture to undergo partial vaporization. A portion of the feed becomes vapor. Okay, we don't know how much is that. And a portion of the feed will still remain as a liquid phase. Okay, and then our goal is to determine the mole fraction. So how much of the components, of each of the components, can be found in the vapor? So, yeah. So we also need to know, so we have a lot of unknowns here. So expect that we need to establish the equations properly. So I will do my best to make this mm, more organized in Excel, because we cannot we may do this um, by hand, but it's not practical. Okay, so we need to use the technologies that we have to solve these kinds of problems. So let's count how many unknowns do we have. 1, 2, 3, 4, and then 5, 6, 5, 6, 7, 8. So we have 8 unknowns. 8 unknowns. Am I right? 1, 2, 3, 4. Okay, just to make sure. Okay, 8 unknowns. So of course, if we need to solve something, we need to make sure that we have equal number of equations. Okay, let's establish the equations first. We can start with a lot of equations. Of course, it will be, it's somehow a pattern for chemical engineering students to start with an overall mole balance for the entire system. So let's start with that one. So overall, okay, mole balance. Mole balance. Okay, for the entire control volume. The control volume is, of course, the flush drum. Okay, so the equation is the feed, it's equal to the summation of the amounts of L and V. So we already know the value of F, which is our basis. So we can declare number 1 as L plus V equals 1, which is the amount of feed in moles. So let's box this equation over here. Okay, so we will get back to that one later. Of course, after establishing the overall mass balance, you need to couple it with the component mass balance. So we are going to create the component, sorry, not mass, it's moles, sorry. So component mole balances. We have 3 components here in the mixture, so we are going to establish 3 components. So let's start with the feed component. So for okay, let's just use that. For component 1, okay, yeah, I will just write the name of the component that corresponds to number 1. It's pentane. Okay, pentane. For pentane, so it will always be, oops, I will just write the format. So Zi multiplied by F. So the mole fraction of the component in the feed times the amount of feed, that's the amount of the component in the feed, multiplied by Xi times L plus Yi times V. So for pentane, we have 0.25. 0.25 times 1 equals X1L plus Y1V. Okay. So, of course, that will be your second equation. 0.25 plus, 0.25 equals the product of X1L plus Y1V. Okay. We can actually, okay. So I will not spend too much time in establishing it in a slow manner, but I hope you will catch up as to why I am writing the component mass balances, mole balances for the other components in this way. My handwriting seems to be skewed or um, inclining upwards. Okay, apologies for that one. I can change. I think I would change the assignment of. You just write it letter A, letter B, just to indicate the sections. And then last but not the least, 0.30 equals x3l plus y3l, y3v. So I hope everybody watching this video was able to, trace how the um, three component mass balances were established. Okay, I hope you were able to follow that part. Hexane and heptane. Okay, there. Pentane. I'll just write pentane again to make it look uniform and organized. Okay, I think it's really skewed. Okay, apologies for that one. The third, or the next part of our um, set of equations will be, we can use the Reals law. Okay, for the Reals law, um, we need to use the values of the k factors. Okay, so remember that Reals law is xi pi vap equals yi multiplied by p. So for us to make use of the k values, we need to re-express the equation in terms of the ratios of the mole fractions of the vapor with respect to the liquid phase. So we're going to create this one, pi vap over p equal to yi over xi, sorry. So we can actually create or transform this portion of the Reals law in terms of ki. So we have yi over xi equals ki. So we're going to establish another equation. So are we done with the x's and y's? Okay, not yet. So this will be technically equilibrium relationships. Xi there. Okay. So I hope you were able to get this part over here. Yeah, as to why we're going to use this one. So instead of using the typical Reals law, we're going to modify the Reals law in terms of the k factors. Okay. So we're going to establish the fifth, sixth, and seventh equation. So for equation number 5, of course, we are going to use pentane. Am I correct? Yes. So we have y1 and then equals k1. The value of your k1 is written above. So 2.7406, 2.7406, and then x1. Okay, for number 6, we have y2 equals 1.0109. 0109 x2. And lastly, for number 7, yeah, the heptane 0.3844 y3 0.3844 x3. So these are the equilibrium relationships, okay, for an ideal solution. Okay, did I include? Oh, I included the numbers, so I will include here. So this will be your 5th, 6th, and 7th equation. Okay, so we lack one. Yeah, we lack one more. Okay, so I think what we can use to further satisfy the equation is we can actually use the 8th equation. What's the eighth? We can actually have 9 equations, but I think the ninth equation is not anymore that useful. C, D, okay. So, oops, I'm using the wrong color. I think the eighth and ninth will be the summation of mole fractions. Of course, that's important. Summation of mole fractions. So there will be a lot of equations that we have to solve simultaneously. Okay, so we need to be grateful enough that even though the problem is somewhat difficult, we have Excel with us to assist us. Okay, so summation of mole fractions, of course, we have y1 plus y2 plus y3 is equal to 1. And then we also have, oh, I need to use number 8, sorry. And then for the number 9, okay, I just realized we have 8th and ninth because y1 and the x and y's. x1, x2, and x3. But actually, in actual mathematical or algebraic, you know, problems, we just need to use 8 equations. But there's an extra 1 equation over here. Okay, so we're now ready to solve everything. So if I were to solve this one in Excel, oops, yeah, are we ready to solve for this one? Yeah. If you ask me, okay, how was I able to get the k values? Yeah, I forgot to mention. Yeah, I forgot to mention. Although the following k values are given already, but they are actually solved from the information given here in the problem. Remember that your ki is equal to pi vap over p, right? Yeah, I'm correct at that one. So the value of Ki is also dependent on temperature because there's a PVAP term here, and the PVAP temperature is, the PVAP term is dependent on temperature. So basically, at temperature of 69 degrees Celsius, I forgot the value of it. Okay, 69 plus 273.15. So we have 342.15 Kelvin. So at this temperature, we can actually get the corresponding values of the PVAPs. I have solved it already, and the values of the PVAPs are 2.721 bar. The value of the P2 VAP is 1.024 bar. And the value of the P3 VAP is equal to 0.389 bar. Okay. So as for the solving of k values, I used the formula for pi vap over p and then substituted it here. Okay. So you can try it on your by yourself. Okay, let's try. 2.7721 over 1.013. Okay, so if we are going to solve that one, 2.71. Oops, I think I used the wrong value for this one. Was I able to get the right answer? Okay, for a while I need to check. 2 point, 2 point, yeah. More or less the same value, but 1 ATM. P, okay. Okay, I think there's a mistake in the value of K1. Let's try to recompute the rest. Okay, we have here 1.024, 1.024, and then, oh no, 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 no. I have a mistake at that one. 1.024, and then 1.013. Okay, let's try to recompute the values. I think there's something wrong with the values. 1.010. Okay, I think I got it right. This one. How about for the K3? So for K3 we have 0.389 over 1.013. Yeah, I got the answer of 0.384. Yeah. I think there's a mistake in the value of K1. We need to recompute this one. Okay, glad I saw this. Yeah. Okay. For P1 we have 2.721 divided by 1.013. 2.6861. 2.686. 2.6861. Okay, I'm actually having a... So that is the correct value for K1. Yeah, I computed it wrongly. 6861. Okay, I will change this. 6861. Okay. So we are already established with the values for, with the equations for the answering of multi-component flash distillation. So how are we gonna do this in Excel? Of course, we need to plug in the unknowns. Just type the cells for the unknowns. So we have 8 unknowns, right? So we can just place it here. 1, 2, 3, 4, 5, 6, 7, 8. So I will make the LNV, okay, be number 1 and number 2. Unknowns number 1 and number 2. And then x1, x2, x3, y1, y2, and y3. Those are the other unknowns. Okay, so of course, when we are going to establish the mathematical relationships, there must be, some trial and error process and everything. So what I would usually suggest is we need to place a dummy value or dummy values for these cells over here, just to, let's say our dummy value for L is 0.3 and then our V is 0.7. So my basis for that one is just arbitrary. As long as I know that when I sum up L plus V, it will be equal to the basis of 1, right? Our basis is 1 mole. We have 1 mole. So if I sum up 0.7 and 0.3 as my dummy values, it should be equal to 1. So yeah. And then for here, I just need to write dummy values as well. 0.3, 0.5, and 0.2. So just making sure that, you know, um, they sum up to 1. They can just, not sum up to 1, because your goal is to do the math and then do the math in Excel, and then the Excel will do the job of adjusting the unknowns for you. For the equations, what we're going to establish are the following. This one. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 equations, but we need to use 8 equations, but we have 9. So we have an extra 1 equation. So that's what we call the dependent equation, and yeah, it's not useful, or we need to just look for one important equation that can help us in solving for the unknowns. Okay, so we can try using this one. L plus V equals 1.
So we can just use that one. We have L plus V. Okay. So it actually depends on you if as to how organized you want to be in Excel. My approach here is just I just want to be very crude and very candid in putting the equations here. So I don't want to be too fancy for now. I will just organize. My usual style is I just want to organize everything after I'm done with the solving. So for number two, I will encode the right side of the equation that I wrote. This one. So I need to follow the formats for this one. Okay, 2, 3, and 4. So I will encode. So x1l plus y1v. Okay, I will do that here. So x1l, x1 times l plus y1 times v. Okay, that will be my number 2. My number 3 equation is x2 times l plus y2 times v. Okay. Next is number 4 is y3 times no, not y3, x3 times l. Okay, plus y3 times v. Okay. I need to check if I was able to okay, blah 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 and then 11. Okay, okay. A good thing. Na 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 na. Okay, and then C10, C6. Okay, I hope I'm doing the right thing. Okay, so it's somehow, I'm doing this like in a really crude manner right now, so no time to polish everything. So I'm done with equations 2, 3, and 4. I will now establish or write in Excel the equations for 5, 6, and 7. So for 5, we have y1 equals 2.6861x1. So what you're going to do here is you will then again write the equations for the following. This one, and this one. So um I will encode that in Excel. So the first one is 2.6861x1. Okay, hope. Okay, plus sorry, 2.6861 times x1. Okay, am I doing it right? 6861. Okay. The second one is 1.0109. Okay. 1.0109 times x2. Okay. And for equation number 7, that is 0.3844 for x3, 0.3844 times x3. Okay, so we have one last equation. Okay. Our last equation, I can just use equation 8 or equation 9. I will just use equation 8 for this one. y1 plus y2 plus y3 equals 1. Remember, in algebra, I mean in basic chemical engineering, I appreciated the dependent calculations in chemical engineering, the dependent equations in chemical engineering calculations. So please remember that one. Okay, so those are the equations and those are the unknowns. I think it would be nice if your L and V's are like not equal to 1 to really force the problem to, you know, be messy and all. Okay, so how are we gonna do this? Okay, so my goal here is to use solver, but in a somehow, you know, a little complicated way. It's not really complicated if you're good in solver, but for if you are a beginner at solver, so you might find it a little confusing. But yeah, we need to make use of only one objective, which is you can just choose any. But remember, we have a lot of equations here, so we need to make all the other equations be heavily involved by putting them or putting the rest of them as part of the constraints. Okay, so on my end, okay, I will try to do this. Hopefully this will work. I will try to choose an objective function, or the objective function, yeah. I will choose equation 1 as our objective function. So that will be my goal. So that's the ultimate goal, to get or to set this value to a certain, to set this equation, or to make this equation here be equal to a certain value. And remember that our equation number one is L plus V equals 1. So I actually change the value of L plus V, make it something that is not equal to 1, to really, force our solver to look for the correct values. So we are going to set the objective of equation number 1 to, and we're going to set this at a value of 1, because that's our constraint here. That's the main goal. Okay, I just chose this one. You can choose other equations as your objective. It depends on you, but this is how I do it. I need to change. Okay, so I think uh you just need to choose. I think you just need to choose 1, 2, 3, 4, 5. Yeah. So what I will do here is, um, in order for us to achieve a value of 1 over here, we need to change this value. We need to change this value. Okay. And we need to choose either the liquid mole fraction component or the vapor mole fraction components as the other variables that we need to change. I will try to change the values of this one, comma, the x2, comma, and the x3. You can also do varying the y1, y2, and y3, but you need to make sure that you only choose one set. You can just choose x1, x2, x3, or y1, y2, y3. You cannot mix the x and y's. Okay. So what are my constraints? For this problem, okay, I need to recall the meanings of the equations here. Yeah, that's a problem if you don't write. Okay, so our goal is to make sure that we hit the following constraints, because these are the stated values over here. Equation 2 must be equal to 0.25, equation 3 must be equal to 0.45, and equation 4 should be equal to 0.30. When you say constraints, these will control, or this will limit the the value of the products and sums that will be obtained by the solver in the right side of this equation. Okay, so for 2.25.3, okay, so this is how you will establish a constraint. So we will add a constraint. For equation 2, it should be equal to 0.25. Okay, it's already added. For equation 3, it should be equal to, what's the value of that one? 0.45. Okay, add. And for equation 4, it should be equal to, oops, 0.30. Oops. Alright. Okay, add. So we have already 3 constraints here. Okay. Oops. For equation 5, 6, and 7, We cannot make them we cannot let them be the constraints, because if you look at the left side is also unknown, right? Yeah, it's also unknown. Okay, it's also unknown. Yeah. This is wait. This is y1, y2, and y3. I think I have a mistake in establishing this equation. Okay, for a while. Yeah, I'll just close this one. If I open it again, well, okay, they will still. Okay. Um. So I chose. I think. Okay, let's review. I chose C5 LV. Okay, x1, x2, x3. Okay. I did not choose y1, y2, and y3, but if you notice, equations 5, 6, and 7, they are, or they should be equal to y1. This one corresponds to y1. This one corresponds to y2, and this one corresponds to y3. Since I chose x1, x2, and x3 as the independent variables that should change, the y1, y2, and y3 should be one of the dependent variables. So I will color this 5 as like the relevant ones. I mean, they are the independent, so they are not connected to any. I mean, they should be the one that these unknowns should be the one that the Excel will get for us. But the y1, y2, and y3, they should be dependent. So it means that these unknowns over here should be connected to the equations over here. So I hope you get my point here. Because if you notice, if I don't do this, there will be no connections between x1 and y1, right? So we need to do this thing that I'm doing right now in order for the x1, x2, x3 to be connected to y1, y2, and y3, because if you notice, we don't have any connections, right? Okay. And last but not the least, we need to make sure that, all right, this one. So we need to make sure that these that the eighth equation, okay, should be the sum of the y1, y2, and y3, which is connected to 5, 6, and 7. Okay. So again, what's important here is really the basic algebra, and then being grounded as to how the cells or how the unknowns are connected to the equations. Okay. So yeah, I cannot anymore delve further into the basic math or the basic logic in the Excel behind this problem, but yeah, I hope you get what I mean. Okay. So, where were we? So we cannot use 5, 6, and 7 as constraints, because if you notice, the left side is also an unknown. Okay, but for this one, for this equation to be tied together, that's why what I did is y1 is connected to 5, y2 is connected to 6, and y3 is connected to 7. And then number 8 is connected to y1 and y3. So there's a loop. So they must be connected to each other. Okay, so the last constraint that I need to do, okay, we have a last constraint. Okay, we need to add. Our last constraint will be, I'm done using this one. We cannot use this one, this one, this. So we're going to use this one. The value of this one should be equal to 1, because equation number 8 is the sum of the y1, y2, and y3. So we have the following constraints. Okay, I hope this works. 1, 2, 3, 4, 5. So we have the goal. We need to equate this to 1. Okay, let's try to check. So this is our objective function. We need to change the values of Okay, am I doing this right? Change this, change this, change this. Okay, and then make sure that your x1 is connected to 2. Okay, make sure that your x2 is connected to 3. Okay, then make sure that they are connected to each other. Yeah, they have a lot of connections with each other. So 5, 6, and 7 is special. Oops, what happened? Oh my gosh. Okay, there, and they're connected. And then y1, y2, and y3 should be connected to 5, 6, and 7. Okay. For number 8, okay. Oh my gosh, I hope this works. Okay, so I will cut the video if this doesn't work. Okay, I can do this. Okay, I'll click now. Oh my gosh. Okay, was I able to get it right? 5, 6, 4, 4. Okay, I have here my answer key, but yeah, the answer is somehow close to the answer key. I will do. Okay, I need to close this other Excel file. I'll save. Okay, solver. Yeah, that's the answer. Okay, so actually, I'm happy that it did not um yield an error. Okay, very good, J. Yeah, ask teacher J. Okay, teacher J is very good today. Okay, all right, I was able to solve it. So happy. So yeah, I hope you were able to get the gist of how I solved it. So let's yeah, so by properly connecting the variables and setting the correct constraints, you can actually solve multi-component distillation problems, whether it will be 3, 4, 5, or more components. So let's finalize our answers. So we have 0.574, 574 moles. Oops. Um, we have 0.426, oh, 426 moles. And then we have, oops, where is it? Okay. Okay, x1 is 0.146448, 146, 0.448. Am I writing the right one? Okay, and 0.407. And the last one, the last set is 0.391. Oh my gosh, I'm just happy right now. I was able to solve it in a crude manner. Yeah, like no preparations in Excel. Just did it organically. I'll call this organically. Okay, I don't know if I'm doing the right thing. I'm saying the right words. Okay, so that's it. Okay, so I hope you learned something for my partial vaporization calculation problems for multi-component mixtures. So you can extend your knowledge in this one to 4, 5, 6, 7, 8, 9, or more components. This works the same way. Okay, so thank you so much for reaching this far, and I hope you learned something from my videos. Okay, goodbye, and see you in my next videos. Bye bye.